a permeable lot that looks like that, okay? We're gonna call that PP for permeable pavement, all right? And next to that permeable pavement is an area that drains. This here is standard asphalt, all right? Remember this one, guys. It's not my fault, it's the asphalt. You get it? Sometimes you just got to love your own jokes. You know what I'm saying? All right, one. And so let's say this has a unit length of 1.0, and this has a unit length of 0.5. This asphalt drains onto the permeable pavement, right? So that means when you think about all the rain that falls onto the permeable pavement plus the adjoining asphalt, all right, you're going to get an equivalent length of 1.5, all right, 1.5, all right, over the infiltrating surface, which is only 1.0, all right? So therefore, the run-on ratio, I'm going to do that run-on ratio, is 1.5. Everyone understand where that comes from? Because the rain that falls on all of this has to be treated and stored only in this. So and that's why we had to take the 35 millimeters and multiply that by 1.5. Is everyone clear with that? When you're doing your homework, well, we're doing the class exercise this afternoon, one of the things I'm going to want you to try to estimate, and it's just an estimate, is what the run-on ratio is for these places that you're picking out. That's why we're going to have multiple tapes, multiple tape measures that you'll use to try to, you're just estimating. We understand that. You're not going to get it exactly right. But you can estimate so you can get some idea of what the run-on ratio is going to be, because that has an impact on how much gravel you need. All right? So that is where the run-on ratio comes from. Now, what I want to spend the next little time doing is talking about some research that has been done. And remember, the reason we do, how many of you do research? You know, a lot of hands. You either do it or you've done it, right? So a lot of you just send it to me reminded why you're doing research. You do research so that designers can do their job better. You got that? You do research so that you give designers a better shot at meeting whatever design objectives. That's most of the research you do. Not some of you doing other research beyond that. And maybe the research you're doing is helping decision makers like politicians or government authorities make better decisions. But your research is always, you're doing it to help someone make a better, more informed decision. All right? That was hot. That's on me. Okay. And so I'm going to share with you some studies that we did that basically enabled people to use permeable pavement in North Carolina. Because prior to that, the government authority was like, oh, we don't trust it. We don't think it's going to work. So the very first example of it that I had that we tried was in a place called Kinston. It has sandy soil, so you can see very high underlying infiltration rates, very high underlying infiltration rates. The seasonally high water table was at least 2 meters from the surface. We didn't try to go any deeper. And it was a simple parking lot. And you can see the type of permeable pavement that we used. It was a concrete grid paver filled with sand, and it was pretty flat. All right. So we did this study because we're like, if it can work, if it can't work here, it won't work anywhere. Like, this is the place it's going to work. And so here it is. We had a big hurricane. The blue is the high hydrograph. The yellow is a hydrograph, the rainfall. And what do you see here? What I'm guessing you see is that for every 4 drops of rainfall, and that was a pretty big storm, 126 millimeters, okay, over the course of a day. For every 4 drops of the yellow rain, we only had 1 drop of runoff. Pretty good. And where a lot of other parts of the city were underwater, this part was actually quite dry. Now, I want to ask you, as you look at this graph, what causes the runoff? Take a look at where we had runoff occur. What is the runoff always associated with? Rain intensity. All right, in this particular case, it rained very intensely. And during the most intense rainfalls, we had runoff triggered. All right. Did the pavement fill up? Did the gravel underneath the pavement fill up? It didn't fill up. And the reason we know it didn't is because we didn't. If the pavement fills up, then what will end up happening is you'll start seeing runoff occur, even during occurring during periods where the rainfall is low. Okay. So that's not what happened. And the reason that it was intense rainfall that caused the runoff to occur is because of what this practice looked like. It was a concrete grid paver filled with sand. It had a relatively low surface infiltration rate. All right. Remember before I talked about 10,000 millimeters per hour? This is not 10,000 millimeters per hour. This is something closer to 50 millimeters per hour, 60 millimeters per hour. And then so we had intense rainfalls that would have triggered, because these are measured in I think 15-minute intervals. So 6 times 4. This is a 24 millimeter rainfall rate, and this is 24 millimeter per hour rainfall rate, and this is almost a 50 millimeter per hour rainfall. So it was the most intense rains that were causing or triggering runoff. All right, but that is necessarily because of the surface covering that we had. Now here's another case where we monitored. I showed you this picture earlier. We had about a half a meter of gravel storage underneath this pavement, so we could store a lot of water in it. We had multiple rainfalls. The largest rainfall we had was 88 millimeters, and we never had any runoff. All right. So that meant that at no point was the rainfall intensity so great that it could overwhelm the infiltrative capacity at the surface of the pavement. All right. And because we had a half a meter of gravel storage, what do we calculate for this one? 18 centimeters up to maybe 0.2 meters at the max. Because we had a half a meter, we were able to capture that entire storm. All right, because we had a lot of gravel storage. All right, and so how well the permeable pavement works is basically dependent on, in terms of how much water it captures, how much runoff it reduces. It's based upon 2 things. Number one, what's the infiltration rate at the surface? All right, if it's I don't know, 1,000 millimeters per hour, then you're not going to have runoff get produced because of overwhelming the surface capacity. All right. And then the second piece is how much gravel storage. Could you eventually fill up a gravel storage? Yes, you can. But because we had a half a meter of gravel, then we didn't fill up that storage at all. All right. Now, the next thing I want to people ask is, if we have different types of permeable pavements, do they reduce runoff? Do some reduce runoff better than others? Well, the answer to that is not really. A little bit, but not really. So we did a study looking at 4 different types of permeable pavement, and we compared them to asphalt. We had adjoining asphalt, but here's our 4 types of permeable pavement. And we looked at them to see how much runoff got reduced. These are the 4 types of pavements that we studied. And you can see that statistically speaking, the concrete grid pavement filled with sand, this one, did the worst, but also, I mean, 98% runoff reduction. That's pretty good, right? So they all worked about the same. One was a little bit worse, but they all worked about the same. All right. Now, so why would you pick one of these? Why would you pick one of these over the other? Well, there's other reasons. This one, we don't pick anymore in America because it's not what we call ADA compliant. And ADA that's the Americans with Disabilities Act. All right. So basically, if someone's mobility is confined to a wheelchair, they have to make sure that what you put on the ground enables someone in a wheelchair to be able to be moved around with some ease. And this pavement type isn't easy for that. All right. So people don't use that anymore, but they do use these types of pavements. And all 3 of them worked about the same. Okay. I keep going the wrong way. Apologize. Now, the next question is people say, hey, does the gap size matter? All right. So the bigger your gap, you're filling your gap with gravel. Okay. Does the gap size matter? Well, what did our studies show? In this particular case, the gap size, basically the area that's filled with gravel, didn't matter if it's 7%, if it's 13%. All right. So I'm glad you guys have your paper out. We're going to do a real quick calculation. I'm going to give you 2 infiltration rates. All right. And I'm going to give you 2 other numbers, and you're going to tell me what the difference in infiltration is for a block. All right. So the block on the left is 13% gap space. The permeability of the concrete block, all right, it's easy. It's 0.000 millimeters per hour. 0. Nothing's getting through the concrete. The permeability of the gap filled with loose gravel, let's go with that gap will have a permeability of 10,000 millimeters per hour. Okay? 10,000 millimeters per hour for the gap filled with gravel. 10,000 millimeters per hour. Okay. Yes. So the 7%, that's correct. So basically, in both pavement types, you have a 0 millimeters per hour infiltration rate associated with the concrete. And then the gap is 10,000 millimeters per hour. Okay? One is 13% gap space. One is 7% gap space. I would like for y'all to tell me what the infiltration rate is for both of those pavements. Because it's a combination of the gap space infiltration rate and the concrete. All right? So how would you calculate that? In America, we put commas to separate groups of 3. 10,000 millimeters per hour. 0 millimeters per hour. Pavement type on the left, it's 13% gap. On the right, 7% gap. 10,000 millimeters at 13%, 10,000 meters, 10,000 millimeters per hour at 7%. If you want the average infiltration rate for the entire block, it's 10,000 millimeters per hour multiplied by 0.13. All right. What's that number? Okay.
With this, with the gap, how 20% gap can take the same amount of the water as 7%?
It doesn't. It's just that the gap itself, the unit that the infiltration rate of gravel in a gap, whatever the surface area is of that gap, is 10,000 millimeters per hour.
And it took the same time.
It's per unit area. It's per unit of surface area. It's per unit of surface area. So the water, okay, another way to put it. If all of this is a gap, and the water falls down, all of this is 10,000 millimeters per hour. If the water falls down on this corner and it's a gap, so the gap's infiltration rate is 10,000 millimeters per hour. The difference between the two pavers is that there's more gap in one and there's less gap in the other. So what I'm not giving you is the average infiltration, surface infiltration rate. I'm only giving you the component infiltration rate. And so however much of the gap, maybe let me go ahead and calculate it, maybe it'll make more sense. So I know that the 13% gap space permeable pavement has an infiltration rate. Can someone just calculate this for me real quick? I think it's 130 millimeters per hour. But if someone was to check me, maybe it's, I think that's right? One more zero, even better. Great. 13, that's right, of course. 1,300 millimeters per hour for this infiltration rate, okay? For the 7%, then that average is, you ready for this? 700 millimeters per hour. All right? 1,300, 700 millimeters per hour. How often does it rain more than 700 millimeters per hour? Hopefully not that often. Hopefully never. So do you see why both gap sizes work fine? Because while the left gap size has a higher surface infiltration rate at 1,300 millimeters per hour, if the maximum rain that you're going to witness is, say, 200 millimeters per hour, that's pretty intense, by the way, 150 millimeters per hour, as long as the number that you see is higher than what the maximum rainfall intensity is, it really doesn't matter, does it? Okay? So how much gap size? You probably don't want to have 2% gap size or 3% gap size. But if you have 5% gap size, and that means 95% of the cumulative footprint is concrete, you're probably okay. All right? Does that make sense? Once we combine, so all that number is per unit, per like square centimeter of gap. That's the infiltration rate associated with that per square centimeter. And so what this calculation shows is basically that the data we got makes sense. All right. As long as you have some gap size, but the key to all of this, all right, what of these two infiltration rates, which one of those can change over time? the 10,000 millimeters per hour, right? And how does that change over time? Well, will it get higher or will it get lower? Lower, you're exactly right. Because what's going to happen? It's going to clog. You got it. And so the trick is how low can you have this go and be okay? All right. We're going to come to that a little bit later, but that's probably one of the most important things that you have to factor in your permeable pavement design is clogging and how low that infiltration rate goes. All right. Just remember that. We will come back to that later. Now, the next thing that I want to mention is your underlying soil. And we talked about this before our tea break. The underlying soil is important, okay, because it's what allows the water that builds up in your pavement to vacate. Okay, so water, there's an infiltrating plane at the surface of your pavement. I don't really have a good example of it. If you think about permeable pavement, I'm going to do a cross section of your permeable pavement. Okay, we got the blocks here. There's like, these are different blocks. Then you got gravel. Okay, this is gravel in here. All right. And then down here, you got your in situ soil. Wait a second. Woo! In situ soil. All right. In situ soil. So water is infiltrating into your in situ soil. All right. After it builds up. And then you also have water as it rains that infiltrates into the surface of your pavement. Now, what I'm going to do is I'm going to bring this down here. Y'all can see that. Okay, so water infiltrates at the top surface, then it builds up at the bottom, and then it infiltrates through the bottom of your permeable pavement. And that's what enables the water to vacate the permeable pavement. Okay, everyone on board with that? So that 10,000 millimeters per hour, that's associated with that surface right there. The underlying infiltration rate, well, that's going to depend on whatever your soil type is, all right? And it also depends on how much construction compaction occurs during the construction of your permeable pavement. All right. Let me show you about how important that might be. So we did a study where the underlying soil, this in situ soil, was between 1 and 2 inches per hour, 25 to 50 millimeters per hour would soak into the ground. All right, as the head built up, basically 25 to 50 millimeters per hour would soak into the ground. Okay, and we thought, oh, that's going to be good. Well, this is the one-to-one line, and all these little dots here, that's the amount of runoff that we observed. Okay, and what we found is, and so we based this design to capture runoff from 1 inch of rain, 25 millimeters of rain. And you can see that once we got to 25 millimeters or 1 inch, we started getting runoff produced, all right? These little black diamonds over here. Well, the slope of this line, that's your pavement storage, right? The slope of your line is your infiltration rate. So we stored all the runoff up to 25 millimeters. And then we looked at water that got released as runoff, and it actually was pretty neatly in along that line. That line is the underlying soil's infiltration rate, okay? So the infiltration rate, which started out as 25 to 50 millimeters per hour, it actually ended up being about 2 millimeters per hour. So it started out 25 to 50, it got reduced to 2. How did that happen? How does the underlying soil infiltration rate, which started out at 20 to 50 millimeters per hour before we did any construction, how does it get reduced to 2? Yeah. Speak real loud. I bet you're right. Yes. Compaction due to construction. You think that happens frequently? You think it happens all the time? If you don't intend to mitigate it, guess what? It happens all the time. You can't drive heavy equipment on top of soil without ruining its infiltration rate. That's what's going to happen. All right. So there are ways to remedy that. All right. And so what people will do is they'll do things like they'll take a bucket, all right, of excavator with teeth. You guys ever watch excavator work? As civil engineers or hydraulic, you should. You should actually be mesmerized. If you're not fascinated by watching heavy equipment work, you're not in the right business. I'm not saying you need to operate that heavy equipment, though that would be a dream of mine. I have done a little bit with those small excavators. My students, I think, worry that we'll break it. It's probably a reasonable concern. Okay? But if you ever watch an excavator come out with its bucket, okay, and then it digs like this, right? Well, you can put teeth on the end of the bucket. You guys ever see excavator teeth? Right. So instead, you can take that arm of the excavator and take that teeth and you go like this on the surface of your soil. And guess what that does to the infiltration rate? It actually makes it a little bit better. It doesn't rebound it fully. You're not going to go from 25 millimeters per hour to 2 millimeters per hour back to 25, but that can go 25, 2 to 5. Okay. And then the other thing that we've seen is what this guy did. He took a piece of rebar. Oh, there's the teeth right there. Took a piece of rebar, affixed it to the bucket. They took that rebar and he just dragged it right through. After he had gotten the compaction, he got the elevation down to where he wanted it. He put him in there, dragged it, and then he moved over about a meter. He went in, dragged it again, and did that across the entire footprint. And what we found is when you do those things, you can take that underlying soil, which if you don't do anything can get reduced pretty easily by a factor of 10, all right, and rebound it, all right, so that maybe perhaps the overall compaction is only a factor of 5. If you're really lucky, a factor of 2, all right, but that is something that you have to do, all right, so just be mindful of that. Now, we also have talked a lot about runoff reduction. Runoff reduction is that which flows off the surface, right? But if you put an underdrain in there, then water can also leave by way of an underdrain, right? That's why you put underdrains in there to begin with. Here's a case where we had something like, so here is the asphalt runoff associated with rain, all right? The little pink, that is a runoff from permeable pavement. So it's an intense rain, we get a little bit of runoff over here. Another intense rain, you get a little bit of runoff. One more batch of intense rain, a little bit of runoff, all right? But then this orange line or yellow line, whatever color you want to associate with that, that's actually water that drains out of the pavement. That's what's coming out in underdrain. So cumulatively, this is for one particular storm, but cumulatively, you can see that while this is rain, P is precipitation, and R is cumulative runoff, all right, you compare it to P to R, this practice does a great job of reducing runoff, right? There's hardly any runoff, all right? But what we do have instead is a fair amount of outflow, okay? And that outflow occurred because we had compacted during construction. So think about all the rain that we had, roughly over 2/3, almost 3/4 of all the rain eventually left, but it left mostly as a result of outflow through an underdrain rather than runoff. Now, would you rather have outflow on underdrain or would you rather have runoff, just in general? Outflow is the right answer. The reason you'd rather have outflow is that means you can do something with it. Because if you have outflow, that means the water has gotten into your permeable pavement and you've captured it. So now as a designer, you can start doing things to help maybe reduce the outflow or reduce the outflow rate. There are things you can do, all right? Runoff, there's nothing you can do. That water is gone, it's escaped. But I do want to point out that in this particular case, due to compaction, we had a fair amount of outflow. All right. 2/3 outflow, 1/3 soaking into the ground. Now, what can you do to improve to lower the amount of outflow volume? And the answer is this. And you're going to see me talk about this some today, and I will talk about it quite a bit on Friday when I discuss permeable pavement. But this is something called internal water storage, okay? IWS. And if any of you ever read any of my papers on bioretention, especially, and some subset of them on permeable pavement, I will talk all about IWS, all right? It is something we use all the time in North Carolina for bioretention. We don't use it all the time, but we do use it sometime for permeable pavement. And the idea is that you pond water inside your practice intentionally. It's internally stored water. Now, that water is not necessarily intended to stay there forever. It's a temporary ponding where the water is basically by pressure head soaks into the ground. Okay? So that's internal water storage. Is everyone comfortable with what this is? All right. So at this same site that we did a study that I showed you the graph of a little bit ago, okay? We were monitoring 4 different types of pavements, all right? Permeable pavements. And all of them had underdrains, type 1, type 2, type 3, all the underdrains. And then all these underdrains drain to a monitoring chamber, okay? Well, one of those 4, and the intention, by the way, was for all of those to have positive slope all the way to the monitoring chamber. Well, we made a mistake. One of those 4 drainage lines, as it was going to the drainage chamber, okay, popped up a little bit. It went uphill a little bit, and then it went into the drainage chamber. So what we ended up doing by accident was we created a little bit of internal water storage. We create a little bit of ponding internal to the permeable pavement, all right? The amount of ponding that we went ahead and we estimated was like 5 centimeters. It wasn't much, all right? It wasn't much, but it was something. 5 centimeters worth of internal ponding. This is the cumulative outflow graph associated with the one permeable pavement type that we tested that had accidental internal storage. And what you'll see is we had very similar amounts of infiltration, all right, or storage, compared to outflow, which is what flowed out the underdrain. In fact, we had slightly more water going into the ground than we did leaving the pipe. That's associated with 5 centimeters of internal water storage. Not much. Remember, in the example that we didn't have internal water storage, it looked like that, where we had twice as much outflow as we had water soaking into the ground, okay? So simply 50 millimeters of storage when we took that, where we had twice as much outflow than infiltration, and we flipped it. Well, not quite flip. We had a little bit more infiltration than we did outflow by accidentally having 5 centimeters of internal water storage. Not that much. Because remember, what's the standard thicknesses? We had 20 to 25 centimeters of gravel storage total, and 5 of them got dedicated to internal water. It's not much, and it made a very big difference. Okay, and so in places where you are trying to improve infiltration, then the idea of having a little bit of an upturned drain pipe to encourage water to soak into the ground is a good thing. Now, there are plenty of places where you don't want that. A lot of times, if you have permeable pavement next to a building, you don't want it. You don't want it to be pushing a lot of water into the ground so that it impacts the foundation of a structure. all right? So I'm not here to give you a blanket, you should always use it. I'm not, but there are going to be cases where having a little bit of storage can go a long way to infiltrating a fair amount of water. In fact, we took this idea and we tried it again on purpose. Remember, that first one was accidental. We tried it again on purpose. In this particular case, we had really big gravel thicknesses, in part because we're using them in the mountains of North Carolina, where it snows, all right? And so we had a standard configuration. We had a really deep configuration where we had 30 centimeters of internal water storage. That's a lot, all right? And then we had one that was kind of in between. We had 15 centimeters of internal water storage, all right? So we had 40 centimeters of gravel, 40 centimeters of gravel, and 15 of those 40 centimeters was dedicated to internal water storage, all right? Then we monitored it. There, okay. So the idea is that we intentionally store water in these. We monitor. There it is getting built. Okay. We rip the underlying subsoil. I'm trying to make it a little bit better. There's your upturned elbow that causes the internal water storage. That's a foot. That's 30 centimeters. Okay, of internal water storage there. And then we installed it and we monitored it. And we monitored it over the course of the spring, summer, and fall. You can see the number of storms that we had. You can see the total amount of rain that fell. It was a very average year, okay, during that time. And I'm going to show you the fate of the water, okay? So let me go back here. We had 53 events occur, all right, that were at least 2.5 millimeters. And of those 53 events, and the one that we didn't do anything fancy to, 8 of them produced outflow. In the one where hold on a second. Oh, darn it. Well, the one we had an upturned underdrain, okay, to force water to soak into the ground. We had one outflow event. And then the one that was really deep, we didn't have any outflow events. The largest storm that hit during that time was 4 inches, so about 100 millimeters. So it had a pretty big storm hit during that window. That's the one that produced some outflow. So you see how well permeable pavement can reduce runoff, especially if you do some things to improve your design. Ripping the underlying soil so that water will soak in more easily, and putting a little bit of an internal water storage feature at the bottom. Even just doing that for 15 centimeters made a huge difference in how this thing performed. Okay. So in the end, if we were to look at the hydrologic cycle associated with permeable pavement and one of our designs, we have our surface layer, which is filled with aggregate. We have an aggregate cross section that has an underdrain. Here's your underdrain. The underdrain will have an upturned elbow, all right, that will force water to be stored internally, all right? And by doing that, you increase your exfiltration. You should have very little surface runoff. You'll have a very little amount of evaporation, very, very little, but like 6% of the water may evaporate. I was impressed by the number. I have some colleagues in Germany that are convinced it's even higher number. Maybe it is there. I don't think it's much higher than 6%, but 6% is potential evaporation. And then the rest of the water will drain out. So this is going to be 1%. That's going to be 6%. This is going to vary. This could be 80%, and this is going to be 15 to 20%. All right? That's sort of an ideal scenario for permeable pavement, and that's where the water goes. That's the fate of the water for permeable pavement. Now, there are some times where you don't want the water to infiltrate. Can you think of a case where that would happen? When would you not want water infiltrating? What's a reason to avoid infiltration? Oh, buy a foundation. That's absolutely one of them. Sure. So from a structural standpoint, absolutely. If the water table, yeah. Yeah, that could be. Yes, actually. If the water table is really close to the surface and you don't want to make it any worse for whatever reason, you would line your permeable pavement. That's true. Thank you. What if the soils or the water that you're trying to treat are polluted? So maybe you don't want your really polluted runoff to soak into your underlying soils. Or maybe your underlying soils have been used for, I mean, there's chemicals or oils that are in your underlying soils because they had storage tanks and stuff like that. Maybe it was an industrial site at one point, and God knows what's got put onto those soils, right? And so basically, there are times you want to prevent pollution from migrating. So those are all reasons that you might want to line your your permeable pavement. All right. And so in those cases, if you line it, you would actually the water. Hopefully, this water here is always present. But then what happens when the storm comes, it pushes out the old water that has been sitting inside your pavement for treatment. All right. And so that is a detention-based permeable pavement system. All right. Now, I want to close on a discussion. I might get into a little more on water quality at the very end. We'll see what time looks like about pavement clogging because it is important. All right, pavement clogging is important. Anyone know where I took this picture? We'll just say somewhere at IIT, rookie. All right. Now, right off the bat, I want everyone to know that this was not intended as a permeable pavement. They did not say, we're going to put permeable pavement here. But if you look at that, is there something about it like, ooh, that's not good? If it were permeable pavement, it wasn't, okay? If it were, you look at that and say, ooh, something's not right. And what is it? What do you see that's a problem? This is your permeable pavement right here. It's not, but imagine if it were. What do you see in this picture that would tell you, oh, that's a problem? If you want your pavement to be permeable. If you don't care, it doesn't matter. Well, I think I'm hearing you say it all. Soil. Soil. You see all that brown dirt. We call it dirt. We call it dirt in America. Soil is where it's supposed to be. Once it runs off, then it becomes dirt. All right, you can call it soil, it's fine. So that would be a problem. Okay. So permeable pavement does run the risk of clogging. All right. And there's a couple of different, there's actually about there's 4 different triggers for clogging. All right. But anytime you have issues where sediment, open sediment, is exposed to your permeable pavement, it is gonna clog. All right. That is going to be an issue in some parts of campus. It just is. All right. Not all the campus for sure, but some parts of campus, exposure to sediment is what is a real killer to permeable pavement. All right. Can tree canopies be a problem? What do trees do? As they grow, do they drop stuff ever? Yeah, they drop stuff. Well, as trees drop stuff, if it's not cleaned up, it will cause things to clog. Okay. In fact, there's an interesting case. This is up in Illinois. This is a very large Illinois, which is outside Chicago. Back to Chicago again. You can see this is a permeable pavement. All right. You can see the trees. Now, Illinois is in the north. They have a decided fall and winter there. I was up in November. So all the leaves had fallen off these trees. All right. You can see some of the leaves collecting right here on top of the permeable pavement. Well, what happens when people take their cars and they drive over this organic debris, this tree detritus? It grinds it in. And you can take a look here at, these are the chimney-filled gravel blocks, and these are the chimneys, the gaps filled with gravel that at one point had a 10,000 millimeter per hour infiltration rate. You think it's still 10,000 millimeters per hour? Nope. It's gone down because detritus has accumulated, cars or tires, whatever, have begun to grind it in, and all of a sudden your infiltration rate goes down. What if it goes down by a factor of 4? So we go from 10,000 millimeters per hour to 2,500 millimeters per hour. Okay, that's still a pretty high number. But what if, in fact, you guys do me a favor, what was the 7% the 7% gap size infiltration rate that you recorded? Was it 700 millimeters per hour? Okay, divide that now by 4. What you got? 180 millimeters per hour. Now, say it again. Yes. What will happen, and that's, so even if you have a really high infiltration rate, with time, if it's neglected, that gap, which had a very high number, still is pretty high. I mean, 250 millimeters per hour is still pretty high, or 180 millimeters is still pretty high. But now you're getting into a point where, oh, we might start getting some runoff. It's a really intense rain. Well, what if you neglect it for a year and now the infiltration rate's reduced by a factor of 10? Then we went from 700 millimeters per hour to 70 millimeters per hour. Is that still pretty good? It's pretty good. Do we have rainfalls in Rookie exceeding 70 millimeters per hour intensity? I would bet all the money in my wallet we do. Okay? And so that's why trees, I don't know why I'm fading in and out, but there we are. That's why trees, I'm going to move this up a little bit. That might help. And vegetation overhanging, it's not an immediate problem. Okay? It's not an immediate problem. It's just a source for clogging that has to be taken care of. You've got to be vigilant to make sure that detritus doesn't build up on top of your permeable pavement. All right. Anytime you have run on, I'll repeat this. Anytime that you have run on, which I talked about up here, okay, you will have clogging. Period. Anytime, even if there's no trees around, anytime you have run on, you will have clogging. Why is that? Because the surface that is running onto your permeable pavement is going to either be a vegetated surface with soil, that's some soil particles and vegetation, vegetated pieces of vegetation will wash their way on eventually, or it's typically asphalt. And as asphalt wears off, what does it secrete? What does it emit? Dust, sand. And so for those of you who've done pavement design, think about the mix associated with asphalt. There is sand in there. There's there's fine soil particles in your asphalt. And as that asphalt wears out, those fine soil particles, when it rains, will wash downhill. Well, if they're washing downhill on top of your permeable pavement, it will cause it to clog. Okay? Now, am I saying this is it's not a bad thing, it's just a normal thing. All right. Some of your pavement is going to clog. If you've got run-on, I don't have any examples in North Carolina where we have run-on that we don't have parts of the lot that are clogged. And it doesn't mean the entirety is clogged. This means that some parts of your lot will clog. Now, I know some of you, how many of you have been to Germany? I've been impressed by a number of folks from India that have made their way to Germany. All right, well, some of you are probably going to go because a lot of folks from here are going to Germany, which is great. If you like beer, Germany is a great place to go. All right, there's other good things about Germany too, but they have great beer. But the word that we use for this clog zone right here, that's a German word, and it's called Schmutzdecke. And Schmutzdecke means dirty roof. Does that make sense? Does that look like a dirty roof to you? It's actually a genius name, a Schmutzdecke, okay? And so guess what the dirty roof doesn't do very well? It doesn't let water flow through very well, all right? And so when you design permeable pavement, you've got to be mindful that a dirty roof, a Schmutzdecke, is going to form, and you have to take preventative action as it's beginning to form to make sure it does not become full-on crusty. Because once that happens, it takes very special equipment, relatively special equipment to break it up. Now, in the United States, we have a lot of equipment where that happens. Now, here's an example of where a Schmutzdecke forms. You can see the asphalt runoff up here, okay? It comes in, and it flows over the permeable pavement. Then it hits this gutter, and then it flows along the gutter line, and then it dumps into the drain. Do you know why that's happened? It's because there is a Schmutzdecke. Everywhere you see water ponding or flowing, there is a Schmutzdecke. And you know where that sand came from and the fine particles that came from that caused that Schmutzdecke to form? It came from the asphalt in the car park. Okay? So we have the pictures I showed you here on campus in Rookie of the roadway, all right, draining onto the parking stalls. It's a good place to use it, but understand that the sediment from the roadway will eventually be that the permeable pavement, if it were put in on the side, would eventually be exposed to the sediment from the roadway, and you'd at least have the beginnings of a Schmutzdecke to form. Okay, so the design associated, there's a way you can design around this, and that's what we do in North Carolina, is we actually limit the amount of runoff. Now, unfortunately, the North Carolina definition is not exactly what I shared with you here, but I'm going to explain it. What that definition says is that the amount of run-on that you can have onto your permeable pavement is allowed to be, let me try again, that the size of the surface that you allow to run onto your permeable pavement is allowed to be up to the exact same size as the surface of your permeable pavement. Okay? So if your permeable pavement is 1,000 square meters, you can, in total, have another 1,000 meters run onto the permeable pavement. And the reason that number was chosen was because it was a balance between trying to get as much water as we can to the permeable pavement and the likelihood of maintenance. All right. So if you knew that you were going to have maintenance happening every month, significant maintenance every month, then maybe you can have your run-on ratio become bigger. Maybe you could send 1.5 times the amount of, maybe instead of 1,000 meters of permeable pavement and 1,000 meters of asphalt. Maybe you could have 1,000 meters of permeable pavement and 1,500 square meters of asphalt. Okay. But North Carolina, we came down to a 1-to-1 relationship. For every 1 part of permeable pavement, you can have 1 part of other surface run-on to your permeable pavement. Is everyone clear on that? Different states in America have different thresholds. My state, North Carolina, is one of the more cautious ones, meaning a lower threshold. There are some states where they'll let 5 parts go to 1. But you know what? In my experience, when you have that high of a loading ratio, it clogs and the pavement doesn't work like it's supposed to. Okay? So as you're going through and doing your groups project this afternoon, I want you to really be mindful of what the loading ratio is. And that's part of the reason why our groups are going to be equipped with measuring tape. Okay? So you're gonna eyeball it. All right, that's an estimate, but we want your estimates to be pretty good. All right. So we're gonna have multiple measuring tapes. We have 3, you think, Swarov? We'll have 2 for sure. Okay. This is how, as a designer, you can limit the likelihood or the rate of clogging. Very important. Now, there are tools out there that do a great job of breaking up the Schmutzdecke. I don't know if any of them are in India yet. Okay. But this does a great job. It's called the Typhoon because it swirls around. You can see where the Typhoon went. Whoop. And you can see where they hadn't put it in yet. Isn't that cool? The Typhoon hadn't run yet. So there are these tools. Now, there's something else I don't have a picture of, because y'all took the picture of me, which I appreciated, but I didn't think to ask for it. But you have these bamboo and cotton, we'll call them not cotton, coconut rakes or brooms. It's possible that those could be used, and I see them on campus all the time being used. It's possible that those could be used at least when you have tree canopy, for sure with tree canopy, to just clear off the deposited leaves. Okay? And so that would be a very simple on-campus tool that you have that if you're worried about clogging due to a canopy, that could be addressed. All right, that could be addressed. The sediment accumulation is more of a challenge to deal with. Not impossible, but it's more of a challenge to deal with. I want everyone to understand that maintenance is an extremely important thing in the whole realm of stormwater control measures. Okay? And I teach a 2-day workshop, equivalent would be 3 days here. Okay? I teach a 3-day workshop just on maintenance of stormwater control measures, and I teach them 5 times a year in North Carolina. And we sell them out every time because maintenance is that important. All right. I know this is a design workshop, and so I'm not going to get much more into the maintenance, but especially with permeable pavement, you've got to have human maintenance to keep it working. Dust. Yeah, that is a great question. Dust can migrate down. Most of the time, the dust gets clogged towards the top, gets caught in the top, though it can go all the way down sometimes. Most of the time, the dust that falls on it become integrated into the Schmutzdecke, which I didn't talk about it, but a fully formed Schmutzdecke is about that big. All right, that tends to be about as thick as the Schmutzdecke gets. All right, so therefore, you've got to have equipment that can break up a Schmutzdecke about, what is that, 30 millimeters? About 3 centimeters thick. All right. So that's important. Now, we have a lot of smart people on this campus, and I've got no doubt that you can get the mechanical engineers and they can make something that could do it. I guarantee you they could do something like that. People are involved in vacuums, any vacuum designers, you could make one that would clear out. You could break up a 30 millimeter thick schmutz stick. Got no doubt. All right. Now, I want to close with the following thing. Is that the more biological, the more ecological a system is, the more built-in resiliency it has, okay? So tomorrow, we're going to spend all day on stormwater wetlands. Would you guys guess that constructed stormwater wetlands are resilient or not that resilient? What's your gut tell you? Yeah, they're very resilient. They have all that vegetation in there, all right? Even if parts of the wetland erode, okay, which they might, you got vegetation that will then colonize the bank and stabilize it. It doesn't happen immediately, but it happens, right? Wetlands are extremely resilient, which is important if you're worried about lots of maintenance. On the flip side, we have this. This is entirely, there's hardly any plants. Maybe there should be no plants. There are some examples where you want to have some vegetation growing, all right? But most of the time, there's no vegetation growing. It's not a resilient practice. If you need it to be functional, it's incumbent upon us as humans to make it work. Okay? But having said that, when I walk around this campus, I'm telling you, I think the practice that probably has the most potential to be used is permeable pavement, which is why I guess I did decide this. It wasn't like Vinny Rossi agreed, which I appreciated, but that's why I decided to dedicate today to permeable pavements. I think it's probably the most applicable practice you can use on campus. Okay, do we have any questions? I have more stuff to talk about, but I think this is a good spot. I wanted to get to about 12:30 today. All right. So when we get back from lunch, when do you want to meet? When I get back at lunch, 2:30? Does that sound good?